Okay, coming to the last application of Gauss law, where we're going to find electric field due to a charged spherical shell. Now, for points outside the shell, we would consider r greater than capital R, where capital R represents the radius of the shell. So let us consider a shell which is charged and let Q be the total charge on it, and let capital R be the radius of this shell. Let P be a point which is at a distance small r from the center of the shell. So we'll construct an imaginary sphere around it of radius small r, which should now act as a Gaussian surface for us. So we have the total electric flux through the entire surface of the Gaussian sphere is given as flux is equal to summation of E into delta S, where E into summation of delta S should give us E into surface area of S. Hence flux is equal to ES cos theta, where we have used vector A dot vector B is equal to AB cos theta, dot product of two vectors. We find out that electric field which is pointing outwards and the surface area at that point P is also pointing out in the same direction. Hence we can say that electric field and surface area vector or area vector, both of them are parallel to each other. Hence theta is equal to 0 degrees, or we get ES cos of 0. Since cos of 0 is equal to 1, we get flux is equal to ES, where S represents surface area of the Gaussian sphere and is equal to 4 pi r squared. Hence you can now directly substitute flux is equal to E into 4 pi r squared. Let us call this as equation 1. According to Gauss theorem, flux is equal to 1 upon epsilon naught times the total charge enclosed by the sphere or by the Gaussian surface. Let us call this as equation 2. Please make sure that this equal to is in between them, a small typing mistake over here. Next, as flux is equal to E into 4 pi r squared and flux is equal to 1 upon epsilon naught times into the total charge, from equation 1 and 2 we get E 4 pi r squared is equal to 1 upon epsilon naught into Q, or E is equal to 1 upon 4 pi epsilon naught Q by r square. This is your expression to find electric field at a point outside a charged spherical shell. Sorry. Next, for points on the surface of the shell, the radius of the imaginary sphere and the radius of the charged sphere both are equal to each other. Hence, we can now write this expression as E is equal to 1 upon 4 pi epsilon naught Q by r squared is 1 upon 4 pi epsilon Q by capital R squared, where both the distances are now same. Hence, E is equal to 1 upon epsilon naught Q by 4 pi r squared, where we know Q upon 4 pi r squared represents surface charge density, where surface charge density is given as sigma is equal to Q upon A, which is equal to Q upon 4 pi r squared. Therefore, E is equal to sigma upon epsilon naught, which is your expression to find surface or electric field on the surface of a shell. Next, vectorially, electric field is equal to sigma upon epsilon naught into n cap, where if E is directed outwards, sigma is positive, and E is directed inwards if sigma is negative. Electric field due to a charged spherical shell for a point which is inside the shell. In this case, small r is less than capital R, or the distance or the point of consideration is inside the shell. Hence, r is less than the radius of the shell. Let us consider this charged spherical shell of radius r, and let this point P be inside the charged spherical shell. This becomes small r. And this shaded part now of radius r represents the Gaussian surface, which is inside the shell. Therefore, the Gaussian sphere, we get a Gaussian sphere at this point. Considering The total electric flux through the entire surface of the Gaussian sphere should be given as flux is equal to E into 4 pi r square. Let us call this as equation 1. And according to Gauss theorem, we have flux is equal to 1 upon epsilon naught times the total charge enclosed by the Gaussian sphere, or the Gaussian surface, where Q represents charge enclosed by the Gaussian surface, where we find out that Q is equal to 0. As seen, the Gaussian sphere or the Gaussian surface does not enclose any charge inside it. Therefore, Q is equal to 0. Hence, you can say flux is equal to 1 by epsilon naught into 0, or it is equal to 0. Substitute this value of flux into equation 1. We get 0 is equal to E into 4 pi r square. As known, the distance cannot become 0. The only term can, and 4 pi is a constant, so the only term that can become 0 is electric field. Hence, E is equal to 0. Now, electric field due to a spherical shell at a point outside is given as 1 upon 4 pi epsilon naught q by r squared, where E is inversely proportional to r squared. At a point on the surface, E is equal to 1 upon 4 pi epsilon naught q by r squared, and is also written as sigma upon epsilon naught. And at a point inside the surface, E is equal to 0. So we have electric field is equal to 0 inside the surface. The variation of electric field with distance r from the center of a charged spherical shell can be understood by plotting a graph of electric field against distance. Now, as known, electric field inside this is 0, and where r is equal to r, let us consider a distance which is equal to the radius of the sphere. So the electric field up to this point is equal to 0. There is no charge inside it, electric field is 0. So from here we have no electric field. So the electric field now, as the distance starts increasing, which should be greater than the radius of the sphere, we get the electric field outside, which is inversely proportional to r squared and should have an exponential curve. So I have E is inversely proportional to r squared, and hence this curve.